Hey everybody, and welcome back to another lesson online. Before we get to it, I just want to say that I know that this is not the most ideal way to learn. I know that this has been probably difficult for many of you guys. We just finished chapter 9, and we took our test there, and I want to say that I was very proud of how many of you took it, that didn't even necessarily need to, how well you all did on it. The Chapter 9 test went really, really well. I know I've talked a lot about this year about learning for the purpose of learning the material and not just getting a grade. And many of you are doing that right now. So I want to say thank you. And keep it up, guys. You're doing well, and hopefully some of this craziness will subside soon. But I just wanted to say that I'm very proud of all you and the work that you guys are doing, so keep it up, okay? We're going to be moving into Chapter 11. We are not going to be spending time on Chapter 10, at least for now. We may come back to it, but as of now, we're going to be jumping into 11, okay? Chapter 11 is called Rationals. The entire chapter is about rationals. We're going to be moving away from quadratics. However, quadratics are talked a lot about in this section. So that's one of the reasons why we're going to be jumping to chapter 11 and skipping chapter 10. And we'll see what we end up doing by the end of the year, but we're going to get right into this. So we're going to look at this little word problem as a little introduction to what rationals are. We have two cubes here. Okay, they're different dimensions, but both of them are three-dimensional prisms. Okay, the question we're going to ask is, which of these use less cardboard per cubic inch of space inside the box? So what we're going to do is we're going to compare the box's surface area to the volume. The surface area is how much cardboard it has, and the volume is the space it has inside. So we're going to take and we're going to divide the surface area, and we're going to divide that by its volume. And we're going to compare this for both different boxes. So the surface area, how do we find surface area? Well, surface area is literally the area that is on the surface. So on this box here, we have a rectangle, which is 4 by a height of 5. So this is 4 by 5, but we have two of those, which are 4 by 5. So the first box, we're going to have 2, which are 4 by 5. And then we're going to add that to, we have a 3 by 5 on the right side, and we have a 3 by 5 on the left side. So we're going to have 2, which are 3 by 5. And then we're going to add that to 2, which are 3 by 4, the bottom and the top. So we have 2, which are 3 by 4. And then we're going to divide this by the volume. Well, you find the volume by multiplying all three dimensions together. So that's going to be 4 times 3 times 5. So this one, to help out, to do it, it reduces to 47 divided by 30 after you do all of that math. 2 times 20, 2 times 15, 2 times 12, add them all together. Now we're going to look at our other box. We have two dimensions, which are 5 by 4. So we have 2, which are 5 by 4. Add that to 2, which are 4 by 6. And then we're going to add that to 2 boxes, which are 5 by 6. Divide that by the volume, which is 5 times 6 times 4. 5 times 6 times 4. This becomes 37 compared to 30. So, which one of these two boxes uses less cardboard for the space inside? The 47 on the top is your surface area, but that's literally cardboard. how much cardboard is needed, and then what's on the bottom is the space inside, the volume. Okay, so again, on the top we have cardboard, and we have on the bottom the space inside, the volume. This one is going to require 47 square inches of cardboard, and you get 30 cubic inches of space inside. This one gives you the exact same 30 cubic inches of space inside, but it uses 37 square inches of cardboard. So that one is our winner. This one right here is going to give you more space inside with less cardboard, or the same space inside with less cardboard. Above, this is an idea of what is called a rational expression or a rational function. A rational function is when you have a polynomial function on the top being divided by a polynomial function on the bottom. If you recall a polynomial can be called a linear or a quadratic or a cubic or a quartic or a quintic. It could have a degree of 1, of 2, of 3. It could have terms. It could be a monomial, a binomial, a trinomial. So the above question utilizes a fraction that has a polynomial both in the numerator and in the denominator. These equations that have a polynomial divided by a polynomial are called rational functions. So, you can simplify a rational function just like you simplify any fraction out there. To simplify a fraction, you divide out the common factor. So let's remind ourselves how to divide out or simplify fractions. So here's a fraction, 42 divided by 18. How am I going to simplify this fraction of 42 divided by 18? We're going to zoom in there a little bit, make that a little bit better to see. So 42, okay, divided by 18. Well, we're going to write out what 42 is. 42 is 7 times 3 times 2. This is called a prime factorization. A prime factorization. We rewrote 42 down to the smallest numbers that divide into it. 7 times 3 is 21. 21 times 2 is 42. Then we can do the same thing with 18. 18 is 3 times 3, which is 9, times 2. Now, if you look here, we have a 3, which is being divided by 3. And 3 divided by 3 is 1. 2 divided by 2 is 1. So these, a lot of people like to say cancel out. I prefer to use the terminology divide to equal 1. So 3 divided by 3 is 1. 2 divided by 2 is 1. What's left? Just 7 divided by 3. We're going to do the same thing with 132 over 36. 132 could be rewritten as 11 times 3 times 2 times 2. We could rewrite 36 as 6 times 6, or you could do it as 3 times 2, which is 6, times another 3 times 2, which is 6. So this is 6 times 6, 36. 11 times 3 is 33. 2 times 2 is 4. 4 times 33 is 132. Again, we're looking for values, prime values that divide out. The 3 is equal to the 3. It goes away. The 2 is equal to this 2. It divides away. This 2 divides away with that 2. The only thing left is 11 divided by 3. Try it again, 227 divided by 14. Now here's the problem. 227 is already prime. 227. Wait, hold on. Is it already prime? Let's take out our calculator here. I know that's a little hard to see for you guys. Okay, but 227. I believe it is prime. Nothing divides into 227. Okay. Definitely not 14. The only thing that divides into 14 is 14. So take 227, divide it by 14, and that doesn't work. Take 227, divide it by 7. That doesn't work. And the only last thing that divides into 14 is 2. That doesn't work. Okay? You can't see any of those. Yeah. So, no, that's better. Maybe a little light. Lower the light. There you go. Okay. So 14 doesn't go into 227. The only other things that go into 14 are 7 and 2, but neither 7 nor 2 go into 227 evenly. So how can we factor this? Well, it doesn't. There are no values that go into 227 evenly. So therefore, we're done. And the reason we're done is there is no common factors. There's no common factors between the numerator and the denominator. Now, this should give you a big old idea of where we're headed. Factors. What did we just get done doing in quadratics? We factored quadratics over and over and over. We factored quadratics. So you're going to be seeing that we're going to be factoring in this unit as well. So, however, there is one major difference between simplifying numerical fractions, these above here, and simplifying what are called polynomial fractions or rationals. Another name for a polynomial fraction would be a rational. When it comes to a fraction, and I know this is excessive here, but you can never, ever, right, have the denominator equal 0. You cannot divide by 0, okay? So, we cannot allow our denominator to ever equal 0. So if there is a value that makes the original rational function's denominator equal 0, you must exclude that value from the function's domain. Now what that means, remember domain. Domain, simply put, is the numbers that can be plugged in. So the whole idea is if this value makes the denominator equal 0, you cannot plug it in. So you must exclude it from the domain. You must state that this number cannot be plugged in. For example, let's look at our first rational expression. It's an expression because it's not equal to anything. But this is our first rational expression, our first rational equation. X minus 1 divided by 5x minus 5. Factor. Factoring is going to be extremely important. Let's look at these. Can I factor x minus 1? Well, no, I can't. There's nothing in common. It's not a quadratic. You can't factor it. But what about 5x minus 5? Well, there's a 5 and there's a 5. So what can I do? Well, I can take out a 5. I can remove a 5. If I redistribute this 5, you have 5x minus 5. But look here. Just like above, the 3 divides out with the 3 and they go away. we have a common factor here. We have a factor of x minus 1, which is being divided by a factor of x minus 1. So this x minus 1 and this x minus 1, they divide away. X minus 1 divided by x minus 1 is 1. So this leaves us with what's on the top, a 1, and what's on the bottom, a 5. But here's the problem. We are now left with a statement, 1 divided by 5. But could my original denominator equal 0? The answer is yes. If you take 5x minus 5 and you set it equal to 0, you add 5 over and you get 5x equals 5. You divide by 5, you get x equals 1. What makes the original problem's denominator equal 0? The answer is 1. This cannot be included in the domain. We must restrict it by saying x cannot equal 1. So this fraction reduces to 1 divided by 5. However, this statement is extremely important, that x cannot equal 1. The reason it cannot equal 1 is because it makes the denominator 0. And x equaling 1 makes the denominator equal 0, which is bad, which is very, very bad. You cannot have that. So you must exclude it. So let's try the next one. Well, if you remember back to our polynomial section, I can simplify this. 3 divides into 21, making it a 7. When I divide exponents, you subtract the value, and there's a hidden 1 up here. So there's 3 a's on the top, there's 1 a on the bottom, there are 2 a's remaining, and both of those a's are remaining on the top. So I have z a squared. However, is there something that makes the denominator equal 0? Can 3a equal 0? Well, it can, if a is 0. I divide both sides by 3. 0 divided by 3 is 0. So if a is 0, it makes my original denominator 0, which is bad. So what must we state? We must state that a cannot equal 0. And there's your answer, 7a squared. A cannot be 0. Let's try a little harder one. In this one, both the top and the bottom factor. I can take a 2 out of the top, and I can take a negative 4 out of the bottom. Now, some of you might be asking, why did I take out a negative 4? Well, I noticed that if this is a minus sign, the only way for them to be the top, same on the top and the bottom, is if this became a minus sign. If I remove a negative, the only way this stays a positive is if this becomes a negative. Negative 4 times x is negative 4. Negative 4 times negative 3 is positive 12. So I had to remove a negative. But look here, x minus 3 divided by x minus 3. This factor and this factor are the same. They divide to equal 1. And 2 divided by a negative 4 is a negative 1 divided by 2. But do not forget your restriction. What makes the original denominator 0? Subtract 12. Divide by negative 4. And the answer is x is negative 3. A positive 3. Positive 3. Negative divided by negative is a positive. So what can x not equal? It cannot equal 3. And there you go. Let's go on to the back page. We're going to try a couple harder problems. You're going to recognize, what do I have in my denominator here? We have a quadratic. I told you that quadratics are going to come back. The reason why we are skipping over into chapter 11 is because they have a lot to do with quadratics, specifically factoring quadratics. And if there's anything that you absolutely need to know to be able to have success in the next coming years in math classes, it is factoring quadratics. It is extremely important you know how to factor quadratics. So that's why we are looking at factoring quadratics. So 3 is a common thing between the first two on the top. So I factor the thing on the top, getting 3 outside of x minus 2. Now let's look at the bottom. What multiplies to negative 6 but adds to positive 1? Well, the answer would be x minus 2 and x plus 3. X times x is x squared. X times 3 is 3x, but minus 2x is 1x, positive 1x, and negative 2 times 3 is negative 6. We factored it. Do you see a common factor? X minus 2 divided by x minus 2 is 1. So the final answer is 3, which is on top, and x plus 3, which is on the bottom. However, you must restrict your domain. So I take the thing on the bottom. Now here's a trick. Take the factored form of it. We're going to take the factored form of what we have on the bottom, and we're going to set it equal to 0. How do I solve this thing? Well, you set both factors equal to 0 separately, just like we did in chapter 9. I add 2 over, and I add 3 over. Or actually not add 3, subtract 3 over. So what are the two things that make the denominator equal 0? Positive 2 and negative 3. But these are things that x is not allowed to equal. If you plug in a positive 2 or a negative 3, it makes the original denominator equal 0, which you cannot do. Let's go to the next one. Another quadratic. Let's factor it. What multiplies to 2 but adds to a negative 3? Well, minus 1 and minus 2. The only thing that multiplies to 2 is 2 and 1, but the only way you're going to add these to a negative 3 is if they're both negative, 1 and 2. Divided by, there's a 3 in common, take that 3 out, leaves behind an a minus 1. A minus 1 divided by a minus 1 divides away, leaving you with a minus 2 divided by 3. However, you must restrict your domain. What can a not equal? The only thing that's going to make this thing equal 0 is if you plug in 1. Positive 1. Because positive 1 plugged in here, 1 minus 1 would be 0. 0 times 3 is 0. Let's try another. Ding, 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 ding. Difference of squares. 4, perfect square. X squared, perfect square. The minus sign in between them. Perfect squares, difference of perfect squares. 2 minus x times 2 plus x. Divided by, take out a 7, leaves behind x minus 2. Now, look here. These are kind of the same, but not really. How do I make them the same? Well, the minus signs are wrong. So let's say I take a minus out of this top one. Well, that would have to make the net 2 become negative, and that negative become positive. A negative times a negative would be a positive 2, and a negative times a positive would be a negative x. So now I have negative 2 plus x times 2 plus x divided by 7 outside of x minus 2. And you can flip the order of these. You can flip-flop these, no problem. And then you have minus outside of a x minus 2, 2 plus x. If your terms are almost the same, but one's negative and one's positive, you can factor out a negative, therefore creating exactly what you want it to be or need it to be. So look here, common factor, common factor. I'm left with a negative outside of 2 plus x divided by 7, which is negative 2 minus x divided by 7. But don't forget to state what it cannot equal. What can x not equal? X cannot equal the original denominator set equal to 0. The original denominator all the way up here, but you can use the factored form, and all you got to do is take the factored one and set it equal to 0. What makes x minus 2 equal 0? Move the 2 over, and there you go. So what can x not equal? 2. X cannot equal 2. All right, try another one. Factor out a 3. We have 3 outside of 1 minus z. I like to put a thing on my z's. Down in the bottom, I have a 2 factored out of a z squared minus 1. Ding, 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 ding. Difference of squares. I told you difference of squares is going to come up a lot. It will. This is a difference of squares. Perfect square, minus sign in between them. So it can factor 2, 1 minus z on the top still, 2 outside of, that is a 2, not a z, 2 outside of z minus 1 times a z plus 1. Again, though, we are almost there. This is a positive 1 minus z. This is a positive z minus 1. How do we fix that? We do exactly what we did on the last problem. I take out a negative. So 3 outside of 1 minus z on the top. Negative 2 outside of a. Now, the z is going to become negative, and the 1 is going to become positive. 1 minus z, 1 minus z. You're left with 3 divided by, you could redistribute that negative 2 if you want to, or you could leave it out. I'm going to distribute it. Negative 2z minus 2. State your restriction. Z cannot equal. What can z not equal? Well, look at your factored form. Do you have more than one factor that has a z in it? If you do, this one could make it 0, and also this one could make it 0. So you must set z minus 1 equal to 0. You must set z plus 1 equal to 0. Add 1 over, and obviously you have z equals 1. Subtract 1, and you have z equals negative 1. What can z not equal? Both positive and negative 1. Those are the two things that would make the denominator 0. Go back up. Again, 3 is in common on the top. 3 gets taken out. 1 minus 3d. Now let's look at the bottom. We have a quadratic here that needs to be factored by grouping. 6 times a negative 1. So I'm going to do this, and I'm going to have to do it by grouping. So 6 times negative 1 is negative 6. What multiplies to negative 6, our target number, but adds to a positive 1? Positive 3 and negative 2. So I split the middle term. So you take the 6d squared, and you split the middle term into positive 3d and negative 2d minus 1. Look at the first two terms only. What's in common in the first two only? The answer is 3d. Take it out of the first two only. That gives you 2d plus 1. But look here, it's a 2d plus 1. Over here, you rewrite the 2d plus 1. And we're going to be having a negative coming out, a negative d. What do I multiply 2d by to get 2d? The answer is just, actually, what am I saying? That would be d squared. It's just a negative 1. Why did I say d? That was silly of me. I apologize, guys. It's late at night. I'm sitting here at 11 o'clock at night doing this because it's the only time I can do it, or else my kids are screaming and stuff. So that's not a d. It's just a 1. Okay? Double check. Negative 1 times 2d is negative 2d. Negative 1 times positive 1 is negative 1. We're good. So our factors are, take out the 2d plus 1, leaves behind a 3d minus 1. That's our denominator, but we need to check this, right? Is it the same as this 1 minus 3d? Again, it's not. The 3d is positive. I need the 3d negative, so what do? I take out a negative. So you have 3 outside of 1 minus 3d divided by negative outside of 2d plus 1. Outside of, this is now the negative, that's the positive, you can flip the order, 1 minus 3d. 1 minus 3d divides away with 1 minus 3d, leaving you with your final answer of a 3 divided by a negative 2d plus 1. You could write that negative on the top. Now we must state our restrictions. What are the restrictions? What makes the denominator 0? This is the denominator, right? This thing right here is the denominator. What makes 2d plus 1 0? Negative a half. And what makes 3d minus 1? Add the 1 over, divide by 3, positive 1/3. What can d not equal? Negative 1/2, positive 1/3. Sorry, that got a little tight there, guys. I apologize. Probably should add a little bit more room, but there you go. All right. Last but not least, another word problem. I know you guys love the word problems. Saying that sarcastically, obviously. Please, guys, try the word problem, okay? Don't ditch all the word problems. Focus on these if you have to. You are choosing between two water baskets that have the same shape, same shape, the figure at the right, same shape as the figures to the right. They both have the same volume. Now that's the key. These two entities have the same volume. What is the height of the rectangular water basket? We're going to look for h. What does h equal? Okay. Volumes are equal. So here we go. We need to figure out the volume of both of these. The volume of a cylinder. The volume of a cylinder is, here's your big equation that you need. You take the area of the base, which is pi r squared, and you multiply it by the height. The volume of a cylinder is pi r squared times h. The volume of this, it's called a prism. You guys can call it a cube, but a cube is where all the sides are the same. But the volume of this is just multiply all three of these together. So we're going to take the cylinder and we are going to set it equal to the volume of the prism. So the cylinder's volume is going to be pi r. R in this case is a squared times the height, and the height is 2a plus 8. The volume of the prism is one side, 2a, times the other side, 2a, times the third side, h. Now, the whole goal is to write your answer in terms of a when we are solving for h. So we're going to rewrite this. We're going to solve it for h, and a's are all going to be on one side of the equation. So don't worry about distributing this. It's already factored. We're going to get a rational that you want to factor, so don't distribute that out. 2a times 2a is 4a squared. So I have pi a squared outside of 2a plus 8 is equal to 4a squared times h. I want to solve it for h, so I'm going to divide by 4a squared. 4a squared divides with 4a squared, just like it divides over here. A squared is going to divide with a squared. Getting what we want, that h is going to equal pi outside of 2a plus 8 divided by 4. You can go a little farther here. There's a 2 in both of these, 2 and that 8. So you could simplify this to 2 pi outside of a plus 4. This 2 then divides into that 4, leaving it as a half. So the answer would be pi outside of a plus 4 divided by 2. State your restriction. A cannot equal, what's the only thing that makes the denominator of 4a squared 0? The answer is 0. A cannot equal 0. And there you go. So big idea on rationals is the denominator cannot equal 0. Just dry. I don't have anything else going on. Throat's just dry. The denominator cannot equal 0. So whatever makes the denominator 0, you must state that. You factor it, and you look for things that are in common, and they divide and go away. All right, guys. Kind of a bigger lesson, especially for one of our first lessons. Biggest idea, factoring quadratics. This is a refresher, a continuation of factoring quadratics. Best of luck to you guys. This will be posted on YouTube, obviously, as you're already listening to it. Try the Math Excel assignment this week. Make sure you get it done by Friday at 8 p.m. And I'll be talking to you again soon. Have a good one, guys.